Okay, welcome everybody to there are everybody to both the CSS 205.1, the Toolkit for Theoretical Computer Science, as well as the lecture series on high dimensional expanders. There are two sets of audiences for this, at least the first set of 8 lectures. So welcome to both of you. So there's a fair number in-person attendees and there's a large number of online attendees also. So before we get started, let me give a quick introduction to both these things. So first, we're going to have a year-long lecture series on high-dimensional expanders, organized by myself, Manish from Math, and Mahesh Kakade from IASC. So these will be lectures happening across different institutes. So this one it will be over the year. It will be very different topics. I've already circulated a web page for this, part of it. The first, so that's essentially going to be on high-dimensional expanders. This is not graphs, but larger dimensional graphs. But as a precursor to that, as a brief intro that we thought we will get started with Spectral, understand graphs and their expansion properties and stuff. So this will be sort of like an initial introduction to expansion. We'll be talking about high dimensional expansion, but we'll start off with the graph expansion. And given that this was going to be covered as part of the Toolkit course, we thought we will start off the lecture series on high dimensional expanders we'll combine the two lectures. So we'll have the same set of lectures, same set of initial 8 lectures that we're going to do. Introduction to spectral graph theory will be for both groups. That's lecture for high dimensional lecture series. I have circulated a web page and you'll have it will be updated weekly on the series of lectures over there. Now coming to the course cases. So this is a course jointly offered by Piyush and myself. And by the way, so for people who don't know me, I'm Prahlad Harsha, faculty at STCS TFR, and Piyush will be a co-instructor. Piyush Srivastava, my colleague at STCS, will be a co-instructor for this course. Of course, he won't be teaching the first. So how does the Toolkit course go? The Toolkit course has several modules, and each module is devoted to a topic. It's a set of tools that we think a typical graduate from STCS should have by the time they get their defense and board. So we introduced you a broad variety of techniques, not necessarily covered in other courses. So it have several modules, each module on a completely different topic. For example, the first module is the module you'll be seeing now. This is going to be the spectral methods and graph expansion. The second one will be multiplicative weight update. We'll have others like concentration inequality, the polynomial method, LP and SDP duality. These will be, and Piyush and I will alternate these modules. The first module is going to be offered by me, and that's how this course will come. And for students interested, you are welcome to attend whichever module you want to, but those who are crediting the course have to attend all the modules. You are welcome to just attend whichever module you would like to attend. Each module will be completely disjoint from the rest. You are free to attend just that sequence of 6 or 7 lectures. Each module will have about 6 lectures. So that's what this course is about. You will once again, I think I've circulated the web page for the course. There's a mailing list being circulated for the in-person attendees for both the HDX lectures as well as the Toolkit. Please add your name to whichever group you would like to be, both, none, or either. Okay. So that's so much for the course. Couple more about things, given that it's the first lecture of the course. So let me start off with just say what's going to be the grading policy of the course. So this course, we'll have 4 problem sets spread across the semester, and these will contribute 60 to 75% of the overall grade. And you will be graded on the best 3 of 4 P-sets. There will be a final exam, which will contribute 25% of the grade. And in-class participation or projects. We haven't yet decided what we're going to have this. This might sort of paper presentation rather. will be between 0 to 15%. That's going to be the breakup of codes. Any questions on logistics before we get into the technical aspects of? Okay, so this is the first module. The first module is on spectral methods here and expansion. What do we plan to do in this? Let me quickly say an outline, and then so it's going to be about 8 lectures. This module will be about 8 lectures, and this will be the part that is common to both the toolkit course and the high dimensional expand. After that, the two things will diverge off, and the plan is to introduce what's the spectrum of a graph, Laplacians, understand random walks on graph, Cheeger's inequality. Let's see a full proof of Cheeger's inequality. The expander mixing lemma. Then the last 2 or 3 lectures will be devoted to actually expander graphs. So as part of this, we will do the zigzag expander construction. So there are other expander constructions, more precisely the Ramanujan expander construction, particularly the construction of Lobotsky, Phillips, and Sarnak. That won't be covered in this module, but there'll be a whole series of lectures devoted to the LPS construction later on in the high dimensional expanders. So this is more or less the topic for the 8 lectures. Okay, so let's get started with today's topic. So what's one? We want to understand graphs. By the whole point of this is we want to understand graphs. Via their spectrum. Okay. I explain what each of these mean. So by the way, it's going to be a very varied audience. So a very varied audience for this lecture series. So it's going to go at different levels. So pace yourself accordingly. Pace yourself. All lectures will be available, will be recorded and put on YouTube. So you can pace yourself accordingly. This is because there are people from CS backgrounds, from math backgrounds, and different backgrounds. So the pace will be, it will be a slightly different pace for various people. So you want to understand graphs, and why do you want to understand graphs? So as a computer scientist, where do graphs arise? Graphs arise. So of course, all of you are on social media. So all of these graphs, the social networks, the friendship graphs or the social networks are huge graphs. These are massive graphs. And we would like to understand properties of these graphs. Question is and we would like to see if the spectrum of these graphs. What do I mean by that? We'll come to that. So let's see few various examples. This is one example of graph. If you're a biologist, possibly you're looking at protein-protein interactions. That's another graph. That is it's a graph in which the nodes are proteins, and it's a weighted graph in which you have edges between proteins depending on the amount of interaction between them. Then circuits, this can be just Boolean circuits, VLSI circuits. Boolean circuits, various this one, you find graphs in these contexts. Various of these. So we'll sort of abstract all of them, and for us, a graph is just going to be G is just going to be a tuple V and E. V is the set of vertices, and E is going to be a subset of E choose 2 is actually unordered tuples, unordered pairs. It's a set of edges. So that's the simplest form of graph will do. We'll later on consider even more this one, in which we look at directed graphs, in which this particular, it's actually an ordered pair. So this just makes it an undirected graph. For now, for simplicity, we'll just focus on undirected graphs. Undirected, and we'll even assume unweighted to begin with. That is, we'll assume that everywhere an edge either exists or does not exist, and if it exists, it has weight 1. What? Sorry. That's weight choose. Yeah, right. Unweighted. If so, typically all the edges of all weights is 1. We might later on talk about later, especially when we go to random graphs, we will talk about weighted graphs. In which we associate the graph will be now a triple VE and a W with a W which is on the edge set. Okay. And what does it mean to look at the spectrum of this graph? Somehow we want to understand properties of this graph. So first thing we're going to do is we're going to associate a matrix with this graph, and then understand the eigenvalues and eigenvectors of this graph, and say what do these eigenvalues and eigenvectors tell you about the graph. That's what all these lectures be. So we're going to associate a matrix with the graph, and understand the eigenspectrum of this matrix. Now, which matrix? So what's the matrix we're going to associate with the graph? Most natural notion, at least from computer science point of view, will be what's called the adjacency matrix of the graph. You'll soon see that that's not the matrix we'll actually be working most of the time. But let's recall. So there'll be actually 3. What are the matrices? Then we're going to be considering actually 3 matrices. All of them will be related to each other. Matrices associated with the graph. And we'll talk about 3 different matrices. One is the adjacency matrix. What is this? This is matrix A. If I want to make the graph specific, I'll put a subscript G, AG, which is a matrix sitting in RV cross V, and AG of U comma V is 1 if the edge UB, if the pair UB is an edge, and 0 otherwise. So typically that's the notice by definition this is a symmetric matrix. That's one matrix. There are 2 other matrices. We will define them as and when come. One is the other matrix which we'll talk about often in this series of lectures is the random walk matrix associated with this graph. We'll possibly define it by the end of the lecture. We will denote it by WG. So. And then thing which we'll be focusing most of our attention eventually will be the Laplacian of the matrix. LG. We'll see why we care about the Laplacian by the end of today's lecture, but for now, let me just define what the Laplacian is. The Laplacian, there are several sort of equivalent or minor differences, but this is what I will call the Laplacian for the most part of this lecture. So we have the AG, which is the adjacency matrix. And then we're going to construct DG, which is a diagonal matrix. This is just diag of the degrees. So dg of u comma v is 0 if u not equal to b, and otherwise it's degree of u if u equals. And the Laplacian is going to be dg minus ag, and you'll soon see why this is a nice definition. Most of the class, actually, when we talk about matrix spectrum, what we'll be talking is actually the Laplacian, not the adjacency matrix. We'll see why that's the case. Okay, so these are the matrices we'll talk about. But when we talk about matrices, I don't want to look at a matrix as a matrix. I want to say there's some operation that a matrix does. So we take a linear algebraic viewpoint of a matrix. The matrix has two different meanings in the linear algebraic. It can either be an operator for some linear transformation, or it can refer to a quadratic form. You can define a quadratic form, and both these things will be useful for us. So we're going to ask about linear algebraic viewpoints of matrices. The first will be that it is an operator corresponding to a linear transform. It's a linear transformation. So it's something which maps RV to RV. We have a this, by the way, for the purpose of this series of lectures, I'm going to only work when the underlying field is reals, and that will suffice for everything. But all of these can be generalized to other fields and stuff. For now, I work on it. And the matrix is going to take some vector phi in this, and you'll be mapping it to M. This one, of course, this is multiplication on this side. We could also consider right multiplication and look at the other direction also. That is phi going to, now this is a column vector, and the matrix is multiplying the column vector. It could be a row vector, in which case the transpose is going to get mapped to. We can do this also, and we will consider both these, especially when we are doing random walks. We'll consider both types of multiplication. Matrix will be both these viewpoints, but let's and then of course is the. So let's quickly see what happens. The adjacency matrix, when you multiply it by phi, what does it do? When AG is the adjacency matrix. So what is AG phi of u? So phi is so AG is the adjacency matrix. Of GVE, and phi is some vector, some v dimensional vector. So what is AG phi of u? I'm just asking what happens with, so you're taking this adjacency matrix, multiplying it by the vector phi, which is phi u1, phi u2, all the way this one. And I'm asking what is the uth entry of this vector? But it's just going to be, no, I just still have to multiply, I'm going to this particular one. So it's just going to be phi of v V being in the neighborhood of U. The adjacency matrix is just going to sum up these quantities. Multiplying by the adjacency matrix just sums up for every vertex, it tells you the sum of these quantities. It's a sort of the sum over this. Okay. So that's what this one does. Let's look at the other operator, the other viewpoint, which is the quadratic form. So what's the quadratic form? So we are familiar with the usual dot product, which from RV cross RV to R, which takes a vector X, a vector Y, and maps it to just summation Xi, Yi. This happens to be an inner product. This is an inner product, and in general, we'll work with any inner product. Inner product is just some bilinear map, taking two vectors and mapping it to a real thing, which is linear on each of them. And furthermore, it's non-negative. The inner product of x comma x is always non-negative, and it is zero only when x is zero. You can work with any inner product. The most typical inner product will always work as this. So we'll work with, most times I'll just work with this inner product, which is a dot product. We might change this later on in the course, but this could be any inner product. And given a matrix, so what do I mean? Given a matrix, I can come up with a new inner, give me a matrix, I can come up with a new inner product. So I can come up with a new inner product, Qm, which is a quadratic form associated with M. What is this quadratic form associated with M? I'm going to map a pair of vectors xy now to x, m, y. So I'm going to not just take the dot product of x and y, take the dot product of x and y. This is in the usual thing, this is just x transpose my. Just to get our hands dirty, if M is actually the adjacency matrix, let's see what is this. What is Qm of x comma y? This is just what I'm asking. It's x transpose Ag y. What would this be? Notice this is summation over u, xu, and Ag y of u. That's the difference. That's the definition of a dot product. Which is what? Which we already seen. This is u, xu. This itself is v, which is neighbor of u, phi v. Sorry, yv. So this is exactly summation of xu times yv for every pair uv that belongs to edges. Okay. One thing to remember is a pair is going to be counted twice, because when I choose u, you will come here. When I choose, I would also done v over here, you will come. So this is actually an ordered. So every pair will actually be counted twice in this. This is ordered pairs. Okay. It's when we look at operators, when quadratic forms, the Laplacian will come much nicer. Let's actually do this even for the Laplacian. Let's see what. So this is the quadratic form associated to the adjacency matrix. It's just summation of, it takes two vectors x and y and maps it to the scalar, which is xu, yv, summation of xu, yv for all edges in which you count an edge twice, uv and vu. You count them both. Okay. Let's do the same thing for, so this is when it was the adjacency matrix. What happens when M is the Laplacian? For now, let's just go with the blind definition of a Laplacian. So we know that M is, the Laplacian is dg minus ag. Therefore, x lg y is nothing but x dgy minus x agy. X agy we already know what it is. So let's try to find out x dgy and then compute the difference. This is a dg is just a symmetric matrix. Therefore, this is just u, the degree of u, xu, yu. That's all this is. So what is I wanted to. Sorry, I was working with a bilinear form. I actually want to work with a. So let's do this. Okay, let's leave it like. What about x? LGY. So that's going to be summation u degree u xu yu minus summation uv and ordered pair xu yv. Okay. Want to know, okay, what happens? What happens when I set x equals y in this? So I'm going to have x lgx. I'm going to have sigma u degree u x square u minus summation that is let's stare at this quantity. I'm going to write this in a slightly different fashion. I want to write this as, let's go over all edges uv in E. Now, when I put this notation, I mean it is an unordered pair. That is going over all edges. I want to write xu minus xv whole square. I want to claim these two are the same quantity. And do you see why? So let's look at the cross terms. Cross terms, you're going to get, in this, you're going to get minus 2xu yu for every unordered edge. Therefore, exactly it appears twice over there. The other term, the square terms, how many times will it appear? It will appear exactly the degree number of times. For every edge, you're going to get x square u per edge. So that's exactly this. So these two quantities are exactly the same quantity. Just stare at it. You're convinced of this? So the nice thing about the Laplacian, it is, so this form. So what do we get this? Get that? What's the conclusion we get out of this? It's this nice form. It's x lgx is always greater than or equal to 0 for all x. So it doesn't matter. This is not true of the adjacency matrix and all. And this is typically so I sort of defined it just abstractly and done it. Typically, a Laplacian comes as an energy of some system, and therefore it will always be non-negative and stuff. And that's why this is defined this way. The Laplacian is a much nicer this one. So as we'll see later on, these will be what are called positive semi-definite matrix. So Laplacian is what is called a positive semi-definite matrix. It's an example of a positive semi-definite matrix, and hence it has nicer properties. In fact, we will be discussing positive semi-definite in detail in some of the later modules. Positive semi-definite is just some matrix whose corresponding quadratic form. If you look at the quadratic form corresponding, if you take M, you're looking at x going to x mx, that's always non-negative for every x. Then I call it a positive semi-definite matrix. And Laplacian has, this is one of the nice properties of Laplacian, which we will be using later on. Okay, so much about matrices and this one. We haven't yet come to our main focus, which is going to be the eigenspectrum. We want to understand the eigenvalues and eigenvectors corresponding to these matrices. So let's quickly recall what we would have seen this eigenvalues and eigenvectors. Let's see a definition for. So suppose for the purpose of this one, I'll focus only on real matrices. You have a real, you can extend this to complex. You have an n cross n real matrix, and P is some n-dimensional vector, lambda is some scalar, which is non-zero, and we have the property that m phi is lambda phi. Then we'll say phi is an eigenvector with eigenvalue b, and the corresponding eigenvalue is lambda. So if there is a pair for a given matrix, if there's a pair phi and lambda which have this property, we call it an eigenvector eigenlambda. Now notice there might be such a pair, there might not be any such thing, there might be multiple of them. What we will be interested is eventually we will look at these eigenvectors and eigenvalues for our given matrix. So we have a graph, we try to take its eigenvectors and eigenvalues and see what it's going to tell us about the graph. That's going to be most of it. So right now I just said this is what is called an eigenvalue matrix. The question is why do
Why is 0 excluded from eigenvalue?
If 0 is excluded from eigenvalue, sorry, 0 is not excluded from eigenvalue. It was a mistake. This is, I don't want this to be the 0 vector. Because otherwise m phi is sorry, you're right. If we can have a 0 eigen value, the eigenvector is, there's no point calling the 0 eigenvector. That's always an eigen. That's a non-degenerate case. That's what I meant. Sorry. Now, do eigenvalues and eigenvectors exist for a given matrix? Of course, this is for a given matrix. The matrix has to have some nice properties for this to happen, but it so happens that all the matrices we will be dealing with, that is matrices coming from graph, the adjacency matrix, the Laplacian, the random walk matrix, will all have a full eigenspectrum. They will actually have n eigenvalues and corresponding n eigenvectors. And this comes from the spectral theorem, which we will not do, but I'll just state what the spectral theorem is. And the spectral theorem, once you know the statement of the spectral theorem will tell you that these matrices are special kinds of matrices and they will have a full eigenspectrum. And then the rest of the course module is trying to take the eigenspectrum of, and I mean eigenspectrum, I mean the eigenvalues and eigenvectors for this, and then try to understand what it tells you about. So what I want to ask is, when do these have? Notice not all. It's not the case that not all matrices have a full eigenspectrum or this one. There's a certain special kind of matrices will have, in particular normal, but we'll have even a smaller set is sufficient for these. One thing to notice about these matrices, at least the Laplacian and the adjacency matrix, these were both symmetric matrices. In general, what we'll show is something like a symmetric matrix over the reals will actually, in fact, symmetric matrices over the reals will always have eigenvalues and eigenvectors. And the spectral theorem is a more stronger statement. What we'll actually show is, so we work with any inner product. Suppose we have, so the spectral theorem, I want to say, guarantees, I'll state the spectral theorem formally, that AG and LG have a full eigenspectrum. That is n eigenvalues and n eigenvectors. The eigenvalues need not be distinct, but they will be, and they will come with certain multiplicity and stuff. So for that, we need to understand. Let's go back to our inner product. We had this inner product, which was nicely defined for us, if you recall. And an example is the usual dot product. Which took xy to x transpose. No? And we also associated a quadratic form, which took x quadratic form. This was from RV to R. It took x to xmx. Let's just study this in the dot product case. Xy being mapped to now x transpose my. Now this can also be viewed. Now this can also be written as x m transpose x transpose y. That's one. So this is also m transpose x y. So it's also the same inner product. It's not just the inner product of x and my. It's also the dot product of m transpose x and y. More generally, we can define the notion of for an arbitrary inner product, can define the notion of an adjoint. The adjoint of a matrix M. This is with respect to some inner product. Could be an arbitrary, any inner product, not necessarily the dot product, some any inner product is the matrix M star such that x my is the same as M star xy. It's that matrix which has this. It's that operator which is going to do this. For the dot product, M star is M transpose. In this case, M star is in fact M transpose. Okay. So that's the definition of an adjoint. Notice adjoint is uniquely defined by this. Because you can just take x to be the EI and y to be EJ. So what will you get out here? You will get M of IJ. This will similarly give you M star of IJ, and that will sort of tell you how to go from there.
This is true for all x and y.
This is true for all x and y. The adjoint is the unique matrix which has this property. Okay. Now, what did we notice about if you work with the classical dot product? What did the adjacency matrix and the Laplacian have? These are symmetric matrices. So they are all self-adjoint matrices. So both the adjacency and Laplacian matrices are self-adjoint with respect to the dot product, standard dot product. And what the spectral theorem will basically guarantee is, if you give me some operator matrix M and there's some inner product with respect to which the matrix is self-adjoint, then there always exists n eigenvectors and n eigenvalues. Definition of let me define self-adjoint. N star equals n. Okay, the spectral theorem. M is some n by n matrix and dot is some inner product such that M is equal to M star. That is self-adjoint with respect to this inner product. Then there exists n eigenvalues, lambda 1 less than or equal to lambda 2 less than or equal to all the way up to lambda n. In fact, real valued eigenvalues. And n eigenvectors P1, P2, Cn. These guys are belonging to R. This belongs to Rn. Such that m phi I is lambda phi I for all I. I'm going to assume this without proof. Lambda I phi. Several remarks necessary at this point of time. So this theorem only says there are, if the matrix is self-adjoint with respect to some inner product, most of the time we'll be working with the adjacency matrix and the Laplacian, and the inner product is the classical dot product. These are self-adjoint, so they will have a spectrum. They will have the full vector, and that's the eigenspectrum we'll be working with. So this is true. You could work with, and the reason I'm stating it this way is when you work with a random walk matrix, we will work with not the classical dot product. We'll work with a different dot product, and then still but it will still be self-adjoint with respect to that inner product, and hence the spectral theorem will tell you that you have a full eigenspectrum. So this is a theorem which will take without proof. But a couple of remarks. Firstly, the eigenvalues are unique up to multiplicities. Unique. That is the same eigenvalue. Some of the lambda i's might repeat, but the number of times they repeat is the same. For a given matrix, that's fixed. Eigenvalues, these are on the set of eigenvalues as a multi-set is a fixed multi-set for every matrix. Is unique up to multiplicity. The spectral theorem will guarantee that. Two. However, the eigenvectors, so the same is not true about the eigenvectors. Eigenvectors, not necessarily. In fact, example, suppose phi1 and phi2 share the same eigenvalue lambda. They are both two eigenvectors with the same eigenvalue. Then notice phi1 plus phi2 is also will be an eigenvector with eigenvalue lambda. Same eigenvalue. Then phi1 plus phi2 is also an eigenvector with eigenvalue. So we will not be able to say eigenvectors are unique for anything. We use the eigenvectors somehow, but we won't be able to say they are unique in any sense. Notice first the eigenvectors can't be unique. If phi is an eigenvector, you scale it, that's also an eigenvector. Just scale it, a fixed scalar, it will also be an eigenvector. But eigenvalues are unique. As a multi-set, they are unique for this one. And then another property which we find you to do is this matrix M. I want to say it has a nice, so far we wrote the matrix this way. I want to say this matrix M actually looks like summation lambda I, phi star. Star for us, for now, let's think of it as just the transpose, this one. So phi transpose is, this is a column vector, this is a row vector, that's a matrix. So this is a rank 1 matrix. Phi star is a rank 1 matrix, and I'm multiplying n, I'm adding n such rank 1 matrix, each of them scaled by the corresponding eigenvector. So these, I'm going to assume, so we'll assume that phi's are actually orthonormal. Do I want to? Let me skip this one for now. Let's skip this part and do this one. So we've seen so much. Before I go further, before we prove any further theorems and stuff, what I thought we will do is actually we will take some simple graphs, look at their eigenvectors, eigenvalue, actually explicitly see their eigenvectors, eigenvalues, and see what they tell us about the graph. So we'll actually plot it. So the next 5-10 minutes will actually change. Once we will look at, I'll stop sharing here. See this? So I just want to plot. Before we prove theorems, I thought we'll actually take some toy graphs, try to understand their eigenvalues, plot their eigenvalues, find out what does actually say the eigenvalues tell you something. So basically what I'm doing here is, this actually I should have said this at the very beginning. This part of the course is based on a similar course taught by Dan Spielman. He teaches a course on spectral graph theory at Yale, and large parts of this, at least the initial, the first 2 lectures will be based off his course. After that, we will diverge, and I'm going to use packages, Julia packages that he developed to plot these. So let's just see what's happening. So this is some. So I'll post all of this online on the course webpage, so you can also play with it. This one. This is just some package that a whole bunch of things that he had on. Just installing the packages. So let's start with some basic things. We'll go to complicated graphs. Let's talk about either a line graph, just a simple graph, a line, a cycle, a complete bipartite star graph. Let's look at how the eigenvalues. This one. So let's say start with a cycle graph on say 12 vertices. And so this is basically, this is a code written by him in which when I instantiate this way, this is and then if I say matrix M, the matrix is instantiated to the adjacency matrix of this particular graph. It's called ring graph. Yes. So that's the That's the adjacency matrix of a ring graph. You can see that. That is, everything will have degree 1. This it's a symmetric thing. That's one. It's the same matrix, just written in non-sparse form. Now let's also write the Laplacian of the matrix. The Laplacian is exactly, it's going to have 2 on the diagonal and a minus 1's 1. So I've asked that eigen is a program which finds out the eigenvalues of the matrix. So it's going to take the matrix corresponding to Laplacian and finds the eigenvalues. Notice it does have, that's a 12 by 12 matrix. It does have all 12. There are 12 numbers over here. It has 12 eigenvalues. And one thing to notice, which we'll see shortly in this one, either at the end of lecture, this one. Look at the smallest eigenvalue of the Laplacian. What is it? It's essentially 0. It's extremely small quantity. It's essentially 0. And this is something we'll notice whichever graph we put in. And we'll see this shortly. Some of you say we made a path graph. That's a path graph. 12. So path graph, everything will have diagonal will all be 2, 2, 2 except the top diagonal and the bottom one. That's those 2 degrees are 1 each. This is also, it has 12 factors, a different set of eigenvalues, but the smallest is essentially 0. Let's plot. Let's ask. So that's the eigenvalues. Now I want to ask an eigenvector. And I'm going to ask, so it also outputs eigenvectors. Now you can ask, what is an eigenvector? They can't be. It's going to give you what we will show is if the eigenvalues are distinct, then what we can, in fact, in your homework problem, if the eigenvalues are distinct, the 2 eigenvectors corresponding to the 2, if 2 eigenvalues are distinct, the eigenvectors corresponding to the 2 eigenvalues will actually be orthogonal to each other. This is not hard to show. And once you see that if all the n eigenvalues are actually distinct, then that means all the n eigenvectors will be orthogonal. Therefore, there will only be dimension 1. So there's only one possibility. Each there's an eigenvector or scalar or scalings of that eigenvector. So this is going to give you all the n eigenvectors. Let's look at a few of them. Let's look at eigenvector 1. Notice eigenvector 1 is more or less the constant vector. It's some constant, it's been normalized. It's made to, all of these are made to unit vectors, therefore it's normalized. Otherwise, it would have been 1, 1, 1, 1, 1. It's normalized, so it's some 1. So eigenvector 2, that's the second eigenvector. That's corresponding to, this is this eigenvector which I plotted is the one corresponding to the smallest this eigenvalue. The first one. Now I'm looking at the eigenvector corresponding to this eigenvalue. Now notice we said, if the first one thing which you will notice for a Laplacian, the eigenvector corresponding to the all zeros will always be a constant eigenvector. The eigenvector will be flat. And this is something we will see by the end of this lecture or not beginning part of this lecture. And once that is flat, and notice I also told you the other eigenvectors, if they are different from this one, they will all be orthogonal. So they all have to be orthogonal. In particular, all the other eigenvectors will have both 0 and both positive and negative quantities, because when they take the dot product with the flat vector, they have the dot product has to be 0. So in fact, you will see that it's true for all the other eigenvectors. You'll see they will be on either side of the origin. So that's the second eigenvector. And I'm just plotting just for this one, the second eigenvector, I'm plotting it. This is the 0 line. It's going from, this is not 0, 0 is over there. Okay. So this is a vertex. I'm plotting vertex against the corresponding value in the eigenvector. Let's plot some more eigenvectors. Let's plot, say, not just plotting the first eigenvector, the second, the third, and the fourth. The first is flat. The second, and all the others are sort of 1, and they will be such that if the dot product of any 2 of them will be 0. And this is true, this will be true for any, this is, we've been doing it for the path graph. Let's change it for the ring graph and you'll have the same sort of. It's a different set of this one, but for the ring graph, it sort of goes this ring graph of the cycle. Here, the flat vector and eigenvectors are also. Now let's do something more interesting. What I want to do. Okay, this is I'm plotting the last eigenvector. So there are n eigenvectors. This is the eigenvector corresponding to the first eigenvalue, second eigenvalue, and so on. Now this is the eigenvector. It was a vertex on 12 nodes. Therefore, there's a 12th eigenvector, and that's the 12th eigenvector. That fluctuates anything there, and this will be common among all the graphs that you see. But let's do something more interesting now. And what I'm going to do is, I'm going to take the eigenvectors and I'm going to plot them on. So I'm going to. So the eigenvectors are two vectors. So I get I get a value. The first eigenvector gives me a real value for every vertex. The second eigenvector gets me a real value for every vertex. Therefore, using the two eigenvectors, I get a pair of values for every vertex. Let's just go and plot that pair on. So now you have a pair on a plane. I can plot those. And then let's connect two things which are an edge. So that's all I'm doing over here. I had a ring and I do plot it. What I will get exactly is what it will do is the ring. Once again, do you follow what's happening here?
Just the first two eigenvectors.
It's just the first two eigenvectors. All I have taken, for every vertex, it's been associated. So what does eigenvector, each eigenvector do? It associates a real number with each vertex. Now, if I have two eigenvectors, I get a pair of real numbers. So I can use this to plot the point on the thing. And I plot the points. And then I also know which are the edge constraints and plot them. And it automatically shapes it out like a ring. Let's do the same thing for the path. You'll see more surprising things later on. And
that plot is on a coordinate system.
Huh? Yeah, there's an underlying coordinate system which I'm not put underneath. It is.
So,
Yeah.
could you go over the last plot again?
Yeah.
What exactly are you plotting?
So, what am I plotting? So, what does the eigenvector give you? An eigenvector gives you a real number for every vertex. It's n-dimensional, it's b-dimensional, gives you a real number. That's the first eigenvector. The second eigenvector also gives you such a thing. So if you take both of them together, they give you a pair for every vertex. I'm just taking that pair, thinking it as a point in the plane and just plotting that point. That's all I'm doing. Of course, you could have taken three eigenvectors, plotted in 3 dimensions, or do it 4 eigenvectors, plotted in 4 dimensions, I could have done various things. Asking you, why do these plots look nice? And you'll see.
Only the case for the first two eigenvectors, or can we take any two eigenvectors?
It won't. We can try that. Any two won't come out.
Also, in
Go ahead.
what cases are we joining the vertices?
If the two vertices, so for every vertex we have a point in the plane. If the two vertices have an edge, we draw the edge between them. The edges are exactly what was given to us of the graph. So what we have done is, I have noticed at this point I have only fed to it the only input is the adjacency matrix of the graph. I told you vertex 1 is connected to vertex 2, vertex 2 is connected to vertex 3. That's all I have told you.
So essentially, we're mapping the matrix to a graph.
We are mapping a matrix to a graph. And it does certain nice things about this. This is just to tell you that the eigenvectors and eigenvalues give you certain. What was?
We didn't see the Laplace.
Huh? By the way, these are all of the Laplacian. These are not of the.
Laplace cell was not run.
Huh?
The Laplace cell was not run.
Yeah, that's fine. That's fine. This should be fine. Okay, that's why it didn't.
It is still a path.
No, this kernel run all or something. Restart and run all that. Let's do the path graph. Yes. Run all cells. I could do it. I don't want to run all the way there. Father, lots of things. Hello. Yeah. Then it plots it like this. That's the same thing. Now let's take slightly more complicated graphs and see what it does. So let's take grids. And the graph is a grid. So I'm taking a 3x3 grid or a 5x5 grid. And I'm going to, it's either a two-dimensional grid. These are two-dimensional grids, these are three-dimensional grids. Let's ask what it does. This is just a toy example to say that the eigenvectors and eigenvalues, even if you just give the adjacency matrix, when you write for compute it, it tells you something about the graph. It comes out with a nice layout of the graph. Why does it come? We'll try to understand that. So this is, let's take a 5x5 grid. So that's just some code written which outputs the adjacency matrix of a 5x5 grid. 5x5 grid has 25 points and it's going to output this. So it's a 25 by 25 matrix. And these are what I have written down here are the first two eigenvectors. V is E dot vectors 2 and 3. I'm not plotting the first two, the second and third eigenvector. These two things I'm plotting. Notice I should not take the first eigenvector. The first eigenvector is a flat eigenvector. So I'm going to take that out. I'm drawing all of the plottings are with respect to the second and third eigenvectors. And let's see what happens when I plot this. It actually does plot it. We will see in the next lecture. This is actually not surprising. It's obvious why it should do this, but we will see why that happens. It plots them nicely. So notice I haven't told it how to plot it. I just gave the adjacency matrix to the graph and it did plot it. Let's take a 3x3 matrix. Let's take a three-dimensional one. So it's a 3x3x3 matrix. I plotted it. Sort of looks like a cube which has been squished. This one. So let's actually now for this case, let's actually plot it in 3 dimensions. Let's take the second, third, and fourth eigenvectors. So we get for every vertex, we get a triple of points and plot this in 3-dimensional. So let us see what that's going to do. What it actually does get. It does get. So somehow these eigenvectors decide to do this. Let's do something more. So what I'm now doing is taking the Platonic solids, the icosahedron, dodecahedron. These are actual solids, regular solids in this one. But what I want to do is just. So for example, this is the dodecahedron. The dodecahedron, that's the input, that's the adjacency matrix. The first vertex, this is an adjacency list. What it just says is the first word, every line is an edge. The first two vertices are connected with an edge of weight 1. The second and third vertex is connected with an edge of weight 1. So I've just taken the dodecahedron. I've written it just as a graph. Forgot about this. And now I feed that. Let's feed that. That's all I'm giving as input to this. And it's reading that graph. It's come out with a 20. It's a dodecahedron is 20. And then let's draw the spectral. This is the 2-dimensional version of it. Let's actually look at the 3-dimensional version. What it does is actually it just plots the dodecahedron. Do this with the icosahedron, which is this one. That's the icosahedron. It actually gets the icosahedron for it. I have all the conics. For example, I have take a cube. These are things which I written down. The cube has 8 things. That's the adjacency matrix of the cube. That's all is being fed to this code. And based on that, I'm going to be drawing this. This is a projective view of the cube. When you draw it in 3 dimensions, you will see. Yeah, it's a particular project. This projective view will make it look like that, the one above. Yeah. Okay, these are just toy examples just to tell you that eigenvectors, when you have a graph, first thing you should do is look at its eigenvectors and they give you useful information about it. At the very least, they tell you how to draw the graph nicely. We'll see why this is the case by the end of next lecture. Questions you want me to run? Of course, these I've also chosen nice examples. This won't be true. Let's do one more example. Let me take. Some of you might be familiar with the Peterson graph. You know what the Peterson graph is? This graph. It's basically this graph. It's a graph on 10 vertices. It has 2 5 cycles, and the 5 cycles are connected in this fashion. And that's actually the Peterson graph's adjacency matrix, which I put in. So the top 5 is the first 5 cycle. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, and 5 is connected to 1. And the bottom 5 is the bottom, so 6 is connected to 8, 8 to 10, 10 to 7, 7 to 9, and 9 to 6. And the middle one, the middle 5 are basically saying 1 is connected to 6, 2 to 7, 3 to 8, 4 to 9. That's what I've done. I'm going to feed the Peterson graph. That's the adjacency matrix. So I've forgotten the whole structure of the Peterson graph. One. Let's do the spectral drawing. It looks weird in 2 dimensions. But let's actually look at it in 3 dimensions. That's actually good. That's the Peterson graph. It's not the usual picture which we see. But this is a much more symmetric picture than what's the usual picture for a Peterson's graph. Okay. Okay. So I'll put this code up and stuff. You can play with it. Want? Let's go back to. All of this was just to impress on you that how much time we have? We have 15 more minutes. So what we'll try to do. So okay, those are just 2 examples which I said to show that the eigenvalue. You take a graph and compute its eigenvalues and eigenvectors. These give you some useful information. It did, for example, it did give you a rendering of the dodecahedron as a dodecahedron. Even though I completely spoiled the structure of it, I just gave the edge connections. It did output the dodecahedron. I gave the cube, it did it. Why does it do it? And all of it, I want to tell you, the eigenvalues and eigenspectrum do contain enough information in it to recover all such things. So we will see some very basic. So what we will do in today's lecture, I don't know if I have time for that also, we'll just try to understand some basic properties of the adjacency matrix. We'll try to look at the adjacency matrix now also has n eigenvalues. What do these eigenvalues? Do they correspond to any properties of the graph? We'll try to see that. And then next lecture onward, actually we'll focus mostly on the Laplacian, which was the one that was used to do all the plotting. So a couple of more remarks I wanted to say before this one. And say that if eigenvalues are distinct, then the corresponding eigenvectors actually orthogonal. In fact, the spectral theorem, not the spectral theorem, will guarantee. These are things which I'm all of these remarks are things which I'm doing without proof. These are just guarantees. That is guarantees for self-adjoint matrices. For self-adjoint matrices. The eigenvectors, there exists a orthonormal basis for the space composed of just eigenvectors. For the ambient space, which is RB of the eigenvectors. What am I going to say? There exists a set of n eigenvectors which form an orthonormal basis for the composed of the n eigenvectors. And in general, when we talk about the eigenvector, we will refer to the basis that correspond this orthonormal basis. We'll fix one basis, we'll work with that. So in general, we'll assume that lambda 1 equal lambda 2 is lambda n. We have phi1, phi2, pn, and we'll assume that pi inner product pj is 0 if I not equal to j and one other. We cannot. Spectral theorem guarantees that there is such an eigenbasis and we'll work with this. Okay. By the way, this gives you a convenient way of writing the matrix. The matrix can now be written as summation lambda I pi pi star for this pi transpose the usual topic. That's a convenient way to write down the matrix. You can write down the matrix. Okay, let's see some. I want to go to one other before I talk about. Before I write properties, I'll need what's called the Rayleigh coefficient. For matrix. So you're given a matrix n. And some vector. The Rayleigh coefficient of R and X is just going to be this is going to work with non-zero vectors. It's how much does the quadratic form scale compared to just when you apply the matrix and when you don't apply the matrix. So this is what I'll call the Rayleigh coefficient. And gives you a nice characterization of this is what's called. So what's the Rayleigh coefficient asking? It's asking how much is the quadratic form scale when I apply the matrix to when I don't apply the matrix. I'm looking at inner product of x with x. How much does it change when I do this? Now, because we know we have an orthonormal basis, what can the minimum of this be?
Eigenvalue.
It will be the smallest eigenvalue. Why is that? Let us just see. So, and for that, if, by the way, is this? Are you comfortable? Why? I don't know how much of linear algebra you guys have done. You're comfortable with this? Why this is the case? So, but this will tell you, what does this tell you? What does this tell you? So once you have this form, so let's try to see. I want to now say, suppose any vector, I give you any vector phi in the basis in thing, I can always write it as in the eigenbasis. So I can write it as ai phi I. It can be written on this. So then what is m phi? M phi is just summation ai m phi I. And what is that? That is just ai lambda I phi I. So multiplying by the matrix M is just going to take the original ai and just scale all the things by lambda i's. Now what happens? Let's look at what was phi, inner product of phi with itself. Because this is an orthonormal basis, this is just summation ai aj phi phi j by definition. But because it's an orthonormal basis, this is one only if I equals j and otherwise 0. So this is just summation ai square. What is phi m phi then? With the same token, this is just going to be summation ai square lambda I. And what we are asking is the ratio between these two quantities. Question is how small can it be? How large can it be? So the Courant Fisher basically says, it should be clear. This is the Courant Fisher. Lambda 1 is in fact the minimum over all x in Rn in the 0 of x mx. This should be clear what we said so far. And similarly, lambda n should be the maximum. In fact, you can do it for each one of these. I'll stop with just these two for now. Okay. But more generally, let me write the other thing. Generally, you can lambda I is the min of all B subsets of Rn. V is this one. Dimension of P is I. You take all I dimension of this one and take the max of x in V. X max x and lambda, and this is also equal to max over all W in Rn. Dimension of W is n minus I plus 1 and min over x W. So V is some subspace of Rn. I'm not taking I'm taking a subspace of dimension. I'm taking min over all subspaces of dimension I.
Dimension of
W, yeah. And those two are just the simple consequences of this. This is lambda 1 is I'm just taking all vectors of all things of dimension 1, in which case there's only one vector in it, so it's the minimum of this quantity. And this is the max. I'm taking the other extreme, that is taking w's of dimension for lambda n. This is just the two extremes. Those the things written there are the two extremes of this, but this is true. And this can be easily got from this characterization. Just looking at this guy over here, you can get the Courant-Fisher characterization. Not going to give it as proof, but this is easy. You should be able to do this from the one. And why am I doing this? This is sort of a useful handle for us to understand the relationship between the eigenvectors and eigenvalues. We will see if I have enough time to do that. Let's just start with the adjacency matrix and see whether these things will. So let's take AG. Now it is symmetric, so it has an eigenbasis. So let us call the eigenbasis mu1 to mu n. I'm going to slightly change this one. Usually we put mu1 to be the smallest and mu n to be the largest. For the adjacency, I'm going to flip it. I'm going to reorder it and have it in this. And that's the usual convention. This is how we put it in. And we'll say these are the corresponding eigenvectors. So these are in R. These are in Rn. Are we? These are the eigenvectors. Yes, in particular, mu1 is what I'm going to call as the largest eigenvalue. Okay. Mu1 gives you some piece of information. I want to say mu1 is actually sandwiched between the largest degree max, and the average. So mu1 is a number, is some real number, which is going to be sandwiched between these two. So in particular, if the graph is regular, we will get that mu1 will be equal to the degree of this. Let's have just 2 more minutes. Let's see a quick proof of this using the Courant-Fisher characterization. And we will stop. So is a statement clear what I'm putting here? So I showed some pictures to tell you that the eigenvectors and eigenvalues tell you something about the graph. And this is one such example. Just looking at mu1 tells you something about the average degree and the largest degree of the graph. mu1 has that encoded in it. We will see more. We will actually, in the next lecture, we will use mu1 and the corresponding eigenvector to actually give a coloring of the graph. Graph coloring is a hard problem. We'll see how to do a coloring using mu1. We'll see that next time. But for now, let's just do this. So what recall once again. So mu1 is the max x agx xx x in Rn. Right? That's the definition of mu1. That's a Courant-Fisher characterization. Now, if I have to show, the reason I'm giving this particular lemma is I'm going to use the Courant-Fisher characterization several times. Suppose I want to show mu1 is larger than degree average. What does it suffice to show? It suffices for us to show that some x for which this ratio happens to be d average. If I show that, then in fact this is true. Now so that's the reason why this is a nice, these characterizations are nice. It gives you upper and lower bounds. And because Courant-Fisher has both an max form and a min form, it will give you bounds on both directions. But let's look at this. So let's just stare at this. So now I have this. I want to show it larger than the average degree. So it's sufficient for me to choose a particular value of x. Yeah, that's obvious. So that sort of takes, that's the first choice which you do. Let's have happen. What happens if you put all ones on the top? So in particular, I want to say this is greater than or equal to all ones, AG, all ones. Yeah. Yeah. What's that? What's huh? At least the denominator is easy. All ones into all ones is n. The numerator is the summation of the degrees. So this is actually degree average. Okay, so that's nice. So Conrad Fisher gave us this property. Actually, I want to say it gives you slightly even better. So if you had put the all ones, we got this. Suppose I put ones which was just on a particular subset and zeros elsewhere. What would I have got? Let's look at the same proof. So instead of one,
We take one of the maximum.
instead of one, we put one restricted to for S is some subset of B. We'll almost have the same proof. We'll get this will instead of n, we'll have size of S. And here, what will we get?
Degree average of S.
So you're looking at just the graph restricted to S. You knock out all the edges outside, completely outside or even going out. You look at just this and asking the average here. So it's the induced average, the average degree of the induced graph. So in particular, even so if you put this, we will get that actually. So mu1 is larger than or equal to degree average of the induced graph of G restricted to S. And this is true for every S. In fact, we get a better lower bound than usual, but just demonstrate. Okay, so this is for the lower bound. What about the upper bound? Upper bound, I want to show that. So we want to show that mu is at most D max. Okay. 2 more minutes, just can stop for this and we'll stop. Right? So in particular, let P1, sorry, mu1 is P1 be the eigenvector associated with mu1. So in particular, what do we have? We have AG of phi1 equal to mu1 phi1. In particular, we have the following. Particular for all u in for every vertex, AG phi1 of u is just mu1 phi1 of u. But what is AG phi1 of u? We saw this. It's the sum of its neighbors. So this is summation phi1 of v, v a neighbor of u, mu1 phi1 u. So I want to say that mu1 is in fact equal to summation phi1 v by v. And this is true for every u in v. So it's true for every u in v. Let's take the u for which this is max. Phi1 of u is maximized. Phi1 of u is set of values. So let u be the argmax of P1 of u. let's U star be the R max. Then that means mu1 is summation phi1 of B. B is a neighbor of U star by phi1 of U star. Now, what do you notice over here? I want to claim this is certainly less than the degree of U star. Because I've chosen this to be the maximum, so each of them is less than or equal to 1. And furthermore, certainly this is less than or equal to degree max. That's fine. When are these two inequalities? Can these two inequalities ever be tied? No. So the proof is done right now. We've already shown mu1 is smaller than degree max. Now, suppose mu1 was equal to degree max. What does that mean? That means this inequality has to be a tight inequality. Equality, this has to be tight. What does it mean that this is tight? All the neighbors of phi1u also have the same value as phi1u. This is not the max, all of its neighbors. Now you can do it with the next guys will also have. So particular, all of them, phi1u will have to become a, where phi1 will have to become a flat vector on the connected component containing the max. The graph is disconnected, I do not know, but all the neighbors, this will just percolate. And furthermore, all of those vertices have to have this degree, because otherwise one of this will become a strict inequality. So in particular, we have also proved the following corollary. If G is connected and mu1 is equal to D max, then G is in fact D max regular. It has to be a regular graph. It has to be fully connected and all the vertices have to have the same degree. This is a very toy example. This is just an example I took to show that looking at even the first eigenvector and eigenvalue gives you some information about the graph. You will see more about this. We'll meet a week from now, next Wednesday, same time. Any questions? Stop the lecture now. Stop the recording now.
No class tomorrow. Usually Wednesday.
Yeah.